morning, everyone. So first, some announcements. Well, if you haven't done the homework, then bring it now or at the end of the lecture. Second announcement: well, the first midterm is coming, and I've written down the main topics for the first midterm. Let's read those aloud. First one is formulating linear programming problem in standard form. It could mean kind of exercise of two types. Either you're given a linear programming form, a problem with different kinds of equalities and inequalities, maybe not all constants are positive, something like this. And the question is formulate the same problem in standard form. Or you might be given some story, like what you did in the homework with blood transfusions or some production. Given some story about the problem, you should formulate it in linear programming form. So basically, use the parameters, explain what the parameters are, and write down all the inequalities and target function so that you maximize the objective function subject to inequalities with this kind of signs, small or equal. Second topic is simplex algorithm. Well, it should be convenient performing it in dictionary form or in tableau form. The exercise might specifically ask you to perform the first 3 steps of the simplex algorithm on such and such problem in tableau form using the largest efficient pivoting rule. So you should be able to understand all these words and perform the actual computation. Next thing is the two-phase simplex algorithm. A problem, linear programming problem without an obvious initial solution, and once again perform the first step or the second step. First phase and the second phase. And finally, some exercises about duality. So here there is a little bit of range of exercises. Well, given a proposed solution to a problem, verify if it is optimal or prove that it is not optimal. Would be solve the primal. So we'll talk about another kind of exercise today. Solve the primal problem using the dual one, or well, given the dual solution, find the primal solution. So any kind of such relation. Basically, you understand what the complementary statement is, how to use it, what the external duality theorem tells you. Say, understand that, say, if the dual problem is unbounded, the original one is infeasible. So all these corollaries or statements should be familiar. You should know how to use them. Well, then that's it. The midterm will have either 4 or 5 questions. It will be during the lecture on Thursday. Okay, I don't remember the date, but it is online. Sorry?
Just next week.
Yes.
It's the 7th.
The 7th. I think it is the 7th. Okay, so any questions about the material for the midterm? So today I wanted to go over 2 things which, well, one thing that I probably have misled you in the two-phase simplex algorithm, or at least, so thanks to the question, I will address it right now. And another thing about duality, how to solve the primal problem using the dual problem. So I'll start with some remarks about the two-phase simplex method. Somehow, first time when I explained it, I used examples which were so short that you, well, would have interpreted what I did in 2 different ways and most likely interpreted it in the wrong way. Maybe well. So let me do one more example and especially emphasize the transition from the first phase to the second one. So the question is to maximize x1 plus x2 subject to x1 minus x2 small or equal to minus 1, x1 plus x2 small or equal than 5, x1 positive, x2 positive. And they also to organize the solution slightly different than what we usually do. So here's the problem. You see that because of the first constraint, the origin is not feasible. If you plug in 0, 0, it's not feasible. So we should perform the. Of course, this problem is simple enough. You can just draw the graph and find the solution. But in general, for such kind of problems, you should apply the two-phase simplex method. So first phase is we'll relax all the conditions. So basically, we'll solve the problem of minimize, that we call the parameter by which I relaxing, maybe W is not W usually used for the dual problem, say A, or artificial parameter. I'll give it a name which is slightly different from the names of the variables, and I also use slight variables. Minimize A, subject to x1 minus x2 minus the artificial parameter small or equal to minus 1, x1 plus x2 minus A small or equal to x1, x2, A, all of it. So I relax each one of these constraints by the amount A, and then I try to minimize this amount A. If I manage to minimize it all the way to 0, then I'm done. So maybe first remark, you do have some freedom right here. I mean, I relaxed all the constraints just because I wanted a procedure which is kind of mechanistic and very simple, applicable to any kind of problem. In fact, I could have left the second constraint as it was. It doesn't pose to me a problem even in unrelaxed form. So if you want, you can forget about the minus A in the second. It will not be, it will not pose a problem. It might even shorten the computations, but just to be kind of, for the scheme to be applicable to any kind of problem without thinking, I just relax all the constraints simultaneously. But of course, if you understand what you are doing, you don't have just to relax all the constraints we do pose the problem. Okay, next I'll formulate this in table format. So once again, it's not necessary, but it's a good idea to get used to solving things in table form. It's faster. You don't have to write as much, and actually the computations are somewhat more organized and somewhat faster. So it's 1 minus 1. Well, for a reason that I'll explain a little bit later, I'll write this artificial parameter in the last column. I'll put it like this, minus 1, minus 1, minus 1, 5. So this column will stand for x1, this column will stand for x2. This will stand for the artificial parameter, the amount by which I decrease everything. And my objective function, let's say z, will be minus a. I want to maximize minus a, so minus like this. And I'll introduce the step variables right here. So here will be the step variables. So that's how I introduce the step variables. I write down such an identity matrix. Or rather, to make this inequality into equality, I should add the step variable to the right side, and then it will become equality. Oh, there are some zeros over here. So in this way, it's obvious kind of which column corresponds to what variables, so that when you come next time and look at this table, you will know what each of this number means. Sometimes people also write the basic variables in the corresponding rows. It's usually not necessary. You can see from the table which variable is basic. Say here it is 1, 0, 0, so this variable is definitely basic. In some cases, when the iterations are degenerate, the table itself doesn't tell you which choice of the variable is basic. Sometimes you might have kind of two columns and they look exactly the same, 1, 0, 0. and which one is the basic, which one is non-basic, we'll have to explicitly specify for no ambiguities. But anyway, for now it's no different from what we do usually. The first step of the two-phase simplex algorithm is actually never, well, is never about trying to increase the objective function. It's about making the initial problem feasible. So it's always about this parameter, the artificial parameter entering this column of minus ones. Entering, and you increase it by a large enough amount so that these inequalities will be satisfied. So here you see that you should increase it at least to 1. You should subtract from 0 at least 1 to get minus 1. And well, here you should not, well, so it's rather minus 1 minus 1 is 0. And here you should not subtract anything, it's already 5. So the basic variable here is already 5. You should not subtract anything. So the only thing which imposes some constraint about A is this one. So this row will be the pivot row here. In general, the pivot row will correspond to the most negative number in the rightmost column here, three coefficients. Okay, next we do the pivoting. So to make this into 1, I multiply the first row by minus 1. I will subtract the first row from the second one. And I'll make this 0 by doing the same. Subtract the first row from the third one. Z plus 1, 0, 0 minus 1, 1 minus 1. Yeah.
How did you get the columns for S1 and S2?
These two. So these are the step parameters. The step parameters are, well, how do I make these inequalities into inequalities? I introduce new parameters, plus S1 here is equal to minus 1. So in general, the left-hand side is smaller than minus 1. I'll make it equal by adding the step parameter. And similarly here, plus S2. Each row has its own step parameter. And then those plus S1 and plus S2 will translate to plus S1 here and plus S2 here. So I have, well, kind of freedom in choosing the names of parameters when I use the tableau method, which I didn't quite have in the dictionary form. In dictionary form, it would be quite a headache, kind of, to see what letter should go to the left, and it will create an impression that different letters have different meaning for the simplex algorithm. Well, they don't. They have different meaning for us. We kind of think about A as artificial parameter, S as step parameter, but for the simplex method, they're all the same. In the tableau form, I mean, you don't write the names of the variables all the time, so you have some freedom to choose the names which are meaningful to you. So this will be the artificial parameter, this will be the step parameters, and this will be the decision variables. Okay, so here we go to this table. We see that now this artificial parameter in the first row is the basic one, and here it's S2. So right now we have the solution where A is equal to 1, S2 is equal to 6. But our objective function is minus 1, we would like to increase it all the way to 0. And we see that there is a way to increase it. We see a positive coefficient in the last row. So it corresponds to the pivot column. And how much can we increase it? Well, the first row tells us you can increase it only up to 1. Second one tells you can increase it only up to 3, 6 over 2. So the first one is the more restrictive. it will be the pivot row. And I'll perform the pivoting. So this is already 1, so I just copy this row. This is 2, so I'll subtract 2 times the first row. So let me show you a small trick. Since we are talking about something that we supposedly already know, we can try to see some shortcuts. So when you are somewhat close to the end, it might be a good idea to start with the last row first. So if you know that you increase z, if the z step increases z all the way to 0, and it's quite easy to see whether it increases. So this parameter will go to 1, and z will go by 1 times 1. So it will increase to 0. So here I'll have z, basically this minus this, or this minus this is z. So z increases to 0. In this problem I know that z cannot increase more than 0. So I don't really have to know what stands here. I already got the optimal solution just because my initial z was minus 8. I know it never can be more than 0. If I go to 0, it's already optimal. And all I have to know is what are the corresponding parameters, well, here. So just find the basic parameters here. One is, so what happens here? This parameter stays basic. I want to know what it is, so I'll have to subtract 2 times the first row from the second one to get the 4 here. This one, well, it stopped being basic, but what became basic is this one, so 0. In fact, this is all I need. So without computing the other numbers, I already can write down the solution. So this corresponds to x2. This basic variable corresponds, I go to here to s2. And all others are non-basic, they must be 0. So in a way, without computing the extra terms here, I can say that my optimal solution will have x2 equal to 1, x1 equal to 0. It is not basic. Let's see whether we got it right. So the next step would be plug it into the original problem and see whether we got it right. So 0 minus 1 is minus 1, 0 plus 1 is smaller than 5. Well, okay, yes. So it is feasible solution. Next question about understanding is, can you tell me what I missed here without actual computation? So I know that I got to the very last dictionary in the first phase of the two-phase simplex algorithm. What should be written here? It's always the same.
All zeros.
Yes, all zeros and minus 1. So here I always write the row z is equal to minus my artificial parameter, because, well, that's what I started with, that was minus the artificial parameter, and I brought z all the way to 0. Oh, sorry, minus 1. Okay. So if I were satisfied with just finding the feasible solution, I would have stopped here and, well, here's a feasible solution. But unfortunately, having made this trick, I will now have to actually compute the full table here because I will use it in the next phase. So phase 2. So in second phase, I know that I start with this solution. So I see that my x2 will be, well, basic, x1 will be non-basic. What other things will be basic? If I compute the first, what happens in the first constraint, it's pushed to its limit, so the corresponding slack variable will be non-basic, but the second variable, slack variable, well, 1 plus 0 is not 5, it's only 1. So the second slack variable will be 4, it will be basic. So I would want to write kind of a dictionary where x2 and s2 are written in terms of the other parameters. So what I didn't emphasize last time is that it is already given to you here. In this last step of the first phase simplex algorithm, you do have a dictionary where x2 and s2 are the basic parameters. Basically, in this dictionary, what you have is, okay, so you know that it's the last dictionary from this row, now it's not important. You also know that A became non-basic. That's very important. It means it is equal to 0, and now you can disregard it. It is equal to 0, and in my original problem, that's what I wanted. I wanted to take A equal to 0. So in the next phase, I can just disregard this column about A. Now I won't have A. I already made it equal to 0. And I will use this very dictionary, which I know a priori that, well, in the last step of the first phase, it will be a feasible dictionary. Otherwise, why did I bother performing the first phase? So it is a feasible dictionary. I will actually use it to initiate the second phase. So the second phase continues exactly where the first phase ends, except that I erase the column that corresponds to the artificial parameter. I already pushed it to 0. So let me go back to here and insert these two numbers. Because we actually computed those 2 and 1. So now my second phase starts with -1, 1, -1, 0, 1, 4, 2, 0, 1, 1. The slight problem is, well, the last row is not what it used to be. In the previous phase, we tried to minimize the artificial parameter, which well, we succeeded, but now we will want to maximize the original objective function. The original objective function is given to you as x1 plus 2 times x2. So it seems like you would have to write x1 plus 2 times x2. But there is a problem with this. So if I want my basic parameters to be x2 and s2, as they seem to be from here. So x2 and s2. I would want to have 0 here and here. Here there is no problem, but here there is no 0. So this table doesn't actually have x2 as a basic parameter. So my first step here will be to translate the expression for the objective function into an expression in terms of the non-basic variables. In other words, okay, so first let me do it here. So try to make this number into 0 by, of course, subtracting 2 times this first row from the last row and doing nothing else. 2, 0, 1, 1, 4. I copy this and I'll make this into 0. 3. 2, 0, z minus 2. So let me, besides this table form, write down what I did in kind of dictionary format. I had my z written as x1 plus 2 times x2. But then I did not want to write it as an expression in x1, x2. I wanted to write it as an expression in the non-basic variables. In x1, which is okay, and s1. I did not want any mention of x2. So what I did was, I want to replace x2 by something in terms of x1 and s1. How can I do this? Well, of course I will go back to here and see that it's written here. x2 is equal to 1 minus plus x1 plus s2 plus s1. So from the first row here, I see an expression for x2 in terms of x1 and s1. And then I arrive at the conclusion that this is 2 plus 3x1 plus 2s1. So this step is, once again, it's not about performing a step of a simplex algorithm, it's about making this dictionary into a dictionary in standard form. So the first step of each of the phases is somewhat exceptional. It's not the iteration of simplex algorithm. In the first phase, it's bringing the dictionary to feasibility, and it always has the pivot column corresponding to artificial variable, the pivot row corresponds to the most negative number on the right. In phase 2, well, the dictionary starts, all the rows are the same as they used to be in the last dictionary in the phase 1. You cross out one of the columns which corresponds to the artificial variable, which is now 0. And the objective function, well, to start with, you will use the original expression. But then you bring this dictionary to the standard form where the variables that you want to be basic are actually basic. So you must produce these zeros. Let me emphasize these 2 zeros. Okay, from here it is the usual simplex algorithm. So maybe any questions up to here? Yeah?
When you write this in a dictionary form, let's say if there is a problem where you need to translate more than one row into in terms of the non-basic variables.
You do it one by one.
So, okay, yeah, so you do it in 2 different steps.
Yes.
Does it matter which one you do first or?
No, it doesn't.
Okay.
The result must be the same.
Okay.
In tableau form, it looks kind of simpler than it is in dictionary. Basically, you have to, you still have to perform several operations simultaneously. Say that this was 2 and this was 3. Then what would happen? You would subtract 2 times the first row and subtract 3 times the second row. So you'll have to still do 2 operations, but you can manage to do them simultaneously. In dictionary format, you probably would want to just do it one step at a time. Remove one of the non-basic variables from here, replace, one of the basic variables from here, replace it by non-basic ones, and then remove the second one. Yeah?
On the midterm, will you say like perform in tableau form or in dictionary form, or do you need?
Yes, I believe that the midterm problem will actually specify which format to use. So you should be familiar with both. And I think that the computational problems are more likely to appear in the table form, and it might be that, say, I don't know, duality problem will be interpret such and such dictionary in terms of the dual or something like this. So we should be familiar with both formats.
How did you get x1 equal to?
X1 equal to 0. So here I just chose all the non-basic variables to be equal to 0. So my default solution, once I get to the optimal dictionary, is set all the non-basic variables to 0, set all the basic variables to whatever they adjust to. So x2 will be equal to 1, s2 will be equal to 4, all the rest 0. x1 is 0, s1 is 0. And what is true is that, this solution which I chose here is not unique. We see from the last row that basically once you set a equal to 0, you do have some freedom with these numbers. The optimality of z doesn't impose to you the solution that say x1 is equal to 0. It could be non-zero. But I do want to choose one solution which is well, kind of basic solution, which is where all non-basic variables are 0 and all basic variables are adjusted accordingly, because I want to use it next to initialize the second phase. And it was obvious to start with that the original problem here will not have a unique solution. I mean, from here you can yes, here you can perform the general iterations, and quite a lot of them, so you might choose basically any column here and make it into a basic one if you want it. So you can do here several general iterations and get to different solutions, but it was obvious to start with that the solution will not be unique, because the solutions to this problem, they are just the physical solutions to the original one. And we know that there are lots of physical solutions to the original one, usually infinite many. So you should expect this problem not to have a unique solution, but out of these solutions, we choose the first basic one that we can choose. So basically you arrive at the first optimal dictionary, where z is actually minus a, and then you set the non-basic variables to 0, basic variables to whatever they adjust from. And then you use it to fit the second phase. Yeah?
What happens if minus a is not 0?
So if here you arrive at minus z minus a,
Yeah, like there's no equal solution.
then you stop right here.
Oh, yes.
I mean, if you arrive at a row where this is z plus 2, say, and here all the coefficients are negative, but not 0, 0, 0, but, well, all the coefficients are negative, maybe 0, 0, 0 minus 1, but here z plus 2, this is not possible, but some negative numbers in z plus 2, then you know that the smallest value of a must be 2. The problem is infeasible, and you stop right here. Right? The original problem is not feasible. Other questions? Okay, so let's maybe finish this computation. Here I can increase z a little bit further. I see that this is the largest coefficient in the last row, so the pivot row will be this one. It's the only one which imposes any constraint, not just the strictest one, just the only one. So I'll make this into 1. Once again, maybe I don't know whether I'm close enough to the optimal solution, but let me start with the last line. If I get all numbers negative here, I will have to do a little bit of computation. So I'll start with z minus. So I'll have to subtract 3/2 of the second row of the last one minus 8, so minus 2 and minus another 6, 0, 0, 2 minus 3/2, 1/2, 0 minus 3/2, minus 3/2. Okay, so unfortunately I didn't get a positive number here. I'll have to make this column this column will be pivot column in the next step, so I'll have to actually compute what I get here. So first row plus 1/2 of the second one. Now I see which row is the pivot row. Once again, only this thing has any restriction. The first one is, you can increase it as much as you want. And finally, or finally, you subtract this row from that one, and you'll get z minus 10 minus 2, 0, 0, minus 1. So I don't know what is the optimal solution. I have all the numbers here are negative. And now I'll just have to figure out which ones are the basic and which are the non-basic ones. So basically, from here I already see that my optimal solution will have x1 equal to 0, s2 equal to 0. The only question is what do I get for x2? So I'll only have to compute this thing, which is 1, 0, and this thing. So, yes, 5. And all the rest I actually don't care about. x2 is equal to 5, and that's my solution. So here I'll have something, but it really doesn't matter what. And it's a good idea to check that you actually get a feasible solution once you get it. So let me see, I get 0 plus 2 times 5 is indeed 10, which is good. 0 minus 5 is smaller than minus 5, and 0 plus 5 is smaller than 5. Yes?
So on the midterm, when we are writing down the tableau for computations, are we also allowed to omit some entries that we don't need? Like you just said for last one.
So it depends on the phrasing of the problem. If the phrasing is find the optimal solution, then yes, perform any tricks that you want, just find it. If the question is perform 3 iterations of the simplex algorithm, then you must have 3 complete tables. Otherwise, it doesn't count. Okay, so maybe any questions?
Is it only the first step on the, I'm sorry, I missed the first of the class, but for our two-phase simplex method, for the first phase, is it only the first step that deviates from the normal tableau table?
Yes. So in the first phase, only the first step is about increasing the artificial variable enough to make everything obviously feasible. So it will enter the basis, and the row which will correspond to the most negative coefficient will be the pivot row. You perform the pivoting, now you get the feasible dictionary.
And then
And
your
then you
tableau table
just-
is normal.
Yes. And there is one thing to remember. In the last dictionary, if you actually get to z equal to 0, the last row must look like 0, 0, 0, 0, minus 1. Basically, z is minus the artificial variable. It will be kind of, if you do get it, you know that you didn't make, well, you are likely, it's likely that you didn't make any arithmetical mistakes in between. If you get it wrong, if z turns out to be minus artificial variable plus minus x1,
What do you mean by z
Something
equals
is-
0? Well, like there's no
Yes.
other.
I mean, this last row here reads z equal to minus the artificial variable, which is exactly what we started with. We started with z equal to minus artificial variable. What I'm saying is that if you arrive at z equal to minus artificial variable minus x1, you know that you made a mistake, because z is minus a, it's not minus a minus x1. It could happen that z is something like 2 minus x1, which for some reason also is equal to minus a, but can never be sorry, minus 2 minus x1. But this can never be larger than minus 2, so we say that it's infeasible problem. The artificial variable has to be at least at most at zero minus
Also, as long as you go back to z without a constant, then that means the two-phase is you found it feasible.
Yes. And also another thing to emphasize this time, which I did not emphasize last time, was you use this last table from the first phase to to feed the second phase. So you basically, once you know that the artificial variable is 0, you cross it out. You use the rest as a feasible dictionary for the second phase. And then the first iteration in the second phase, the second iteration in the second phase is also a little bit exceptional. So the first iteration in the second phase, it's only kind of, the only thing it's doing is convert the objective function into a form which uses the non-basic variables only. So you convert these non-zero entries which correspond to basic variables to 0 variables addition, and then the usual simplex algorithm. Okay, other questions? Yeah.
In the first phase, you choose the pivot row, which corresponds to the most negative entry in the last column, whereas in the second phase.
In the second phase,
Choose the pivot row there.
so here the first step was not about performing a pivoting. I only changed one row. I didn't change, well, anything in the basic dictionary. I only changed the expression for the objective function. So here I looked at these two numbers and I wanted to make sure that they are both 0. Why did I want it to be 0? Because I want x2 and s2 to be basic variables. So this must be 0, and then I just subtract the corresponding multiple of this row and the corresponding multiple of this row. So it's not about making a pivot. I don't have a pivot row, don't have a pivot column, it's just, I mean, in a way, kind of, these two columns are pivot columns, but it's not really, I don't really think about it this way. I just want to make these numbers into zeros.
Okay. And then for
The next one is the usual simplex algorithm.
Oh.
It's no different from the usual steps. Other questions?
If you were pretty confident there was a feasible solution, could you just start with the solution 0, 0, 0, don't do phase 1, and then just try and like do the same thing as you did in phase 1 here, just try and make it feasible? I mean, like, you obviously wouldn't have an obvious way to do that
Yes, so
necessarily.
that's my problem, because I will be kind of moving in the dark
Yeah.
and hope to get lucky and find a feasible solution. Yes, I mean, on small problems it might be a good strategy, it might save you time. On large problem it might, I mean, it is equally likely to lead you astray, kind of. It really does that right.
But that could work.
It could work, yes.
Yeah, so if you like by chance get lucky, find a feasible solution, you can skip the 2 phase, right? Then go sim, right, straight.
So that, it doesn't sound like a good strategy to hope to be lucky. It's likely not to work.
Even if you find a physical solution in the beginning without minimal phase, I don't think you can continue the simplex method because don't you
No,
need...
I mean, if you find the original feasible solution as he suggested by performing some iterations of the simplex algorithm, you're guaranteed to find a basic feasible solution, one that corresponds to some dictionary. And then you can...
because if you just found any solution, like all of them are non-zero, let's say, then there's no way to continue the simplex method, right?
So
So you need zeros always.
yes, so think about the picture associated to guessing. If you feed the simplex algorithm with some feasible data, you basically say that this is your region, and what you do is, well, you start with one non-feasible solution, you might jump to another non-feasible solution, and then to a feasible solution, and voila, now you have a way to start the simplex method. If you just look at the problem and start guessing some numbers which will fit, you're likely to get right here. In this case, there is still a way to find a basic feasible solution. Basically, increase the first variable until you hit some constraint, and then try to take this constraint into account and increase the other variable until you get to some corner. So this also works, but once again, it's a strategy which depends on you being lucky, and I don't want to discuss it because, I mean, in a large room of people, some will not get lucky. Okay, other questions? so another thing I wanted to discuss today is slightly different kind of problem about duality. I taken the example from the book, and it's exercise 5.2 in the book. And the exercise is solve the problem to maximize minus x1 minus 2x2 subject to, and now there are lots of constraints, minus 3x1 plus x2 small equal than minus 1, x1 minus x2 small equal than 1, minus 2x1 plus 7x2 small equal than 6, 9x1 minus 4x2 small equal than 6, minus 5x1 plus 2x2 small equal to -3, 7x1 minus 3x2 small equal to 6, and x1 x2 equal to 0. So this problem, I mean, a priori it looks like it is very usual problem. You just apply the simplex method. In this case, it would be two-phase simplex method because we have two constraints which are for which the origin is not feasible. Well, it will take lots of computations. Basically, if you recall, we once discussed how many iterations the simplex method has typically, and it was like this. It was the number of constraints times the logarithm of number of variables. So times some constant. So here you have lots of constraints and just a few variables. And it's really bad because the number of constraints, the more constraints you have, the more iterations you have, it grows linearly. It would be nicer if you could convert it to a problem about lots of variables, but few constraints. Because the number of iterations in the simplex algorithm scales like a logarithm of number of variables. So, well, how to do this? It turns out that you can basically by using the duality. In duality, what used to be kind of rows of a matrix become columns of a matrix. So basically it will become such a problem. Very long, but not very high versus very high problem like this. So the idea is solve formulate and solve the dual. So let's do this. I want to minimize W, which is minimize the linear combination of these numbers, minus y1 plus y2 plus 6y3 plus 6y4 minus 3y5 plus 6y6 subject to the constraint that this linear combination of this coefficient is at least -1, and for the second one it's at least -2. So it's subject to minus 3y1 plus y2 minus 2y3 plus 9y4 minus 5y5 plus 7y6 is at least -1. And similarly for the second variable, y1 minus y2 plus 7 times y3 minus 4 times y4 plus 2y5 minus 3y6 is at least -2. And I want both to be positive. So now look at this problem and observe two things. First one, well, we did manage to make it into a problem with few constraints but lots of variables, which, well, usually is a good idea. It's a better idea than such a problem. It usually leads to much fewer iterations of the simplex algorithm. Another thing, quite miraculously, this dual problem turns out to be feasible to start with. I mean, the origin is feasible for the dual problem. If you plug in 0, 0, 0, 0, 0, 0 as y's, you'll get that 0 is indeed greater than -1, 0 is greater than -2. So even though the original problem didn't have the origin as feasible, the dual one, well, happens to have origin as feasible, so we got lucky here. It's not usual, but basically, if the original objective function has all the coefficients negative, then it is always like this. Okay, so now let's try to solve this problem. We won't have to do the two-phase simplex algorithm, just the usual one. So we have to convert this into standard form. So basically multiply both constraints by -1. I don't want the greater or equal sign. So copy these numbers, but with negative signs. 3, -1, 2, -9, 5, -7, 1. Second one will be -1, 1, -7, 4, -2, 3, 2. My objective function W. Well, I want to minimize this expression, which is to maximize the negative of this expression. So it will be 1, -1, -6, -6, 3, -6. And I will introduce the slack variables right here. So I copy a small identity matrix. So just notice that here the slack variables are just kind of the addition of 2 by 2 matrix. If you were to go to the original problem, just the slack part of the matrix would be a 6 by 6 matrix. Awful. Huge. But this one is manageable. So we can write down what columns correspond to what variables. Once again, it's not necessary, but it's a good idea if you want to revisit this computation ever later. It's a good idea for you to understand which column corresponds to what variable. Okay, now let's follow. Yeah.
Why did you change the signs from the?
So for the constraints, I changed the signs because of this inequality.
But what the objective?
Because I wanted to minimize this,
Right.
but the standard linear programming problem is about maximizing. So I want to maximize negative of this. Okay, so this problem will just follow the usual procedure. Choose the largest positive coefficient. This will be the pivot column. The pivot row will correspond to the strictest constraint. This doesn't impose one. This does. So this is the pivot row. Let's make the pivoting. So it will be, I'll have to subtract 3/5 of this row from the last one. Zero minus 3/5 minus 6 minus 3/5 and so 21 minus 9 0, minus 6, 3 distances, minus 3 fifths, minus 6 minus 24 over 5, minus 3 fifths, it's minus 2 fifths, and 1 minus 3 fifths like this, so it's minus 4 fifths. So I hope we didn't make a mistake. 4 fifths, 2 fifths, 3, yes, looks right. And what's good is that already in the first pivoting I got all the coefficients being negative, so I know that, well, I won't have to do too many computations from here. I know that this will correspond to 1, 0, this will correspond to 0, 1. I will want to know what are these, especially what is this variable. This corresponds to the slack variable T1. This corresponds to y5. So I do want to know what y5 is. I don't really care about the slack variable. Maybe I do. So let me compute both these numbers.
So is it that T2?
This is, I think it is T1. Oh, sorry, no, of course T2, yes, you're right. This T2, yes. So, this one, 1 minus whatever times 0. That's good, thanks. So I do want to know what are these variables. All the rest will be equal to 0. I don't want to compute all the other numbers. These ones I do want to compute, so this will be 1 over 5. And this will be, I'll have to add 2 fifths of the first row, so 2 plus another 2 over 5, so it's 12 over 5. So I see my solution to the dual problem. So once again, here I have something. Solution to the dual problem is y5 equal to 0, y5 is equal to 1 over 5, T2 is equal to 12 over 5, the rest equal to 0. Well, the problem with this is I did not yet solve the original problem. I solved the dual, so if this was about the production problem, it means I found the shadow crisis, but I don't know what is the optimal production of that. It's really not good for the solution. So now, how can I go back from the solution to the dual problem to the solution of the original problem? Complementary slackness, yes. So complementary slackness tells me every time I have a non-zero variable here, I will have a corresponding zero variable in the original problem. Here I have 2 non-zero variables, y5 and t5, what they correspond to. So y5 corresponds to what variable? It corresponds to the, yes, to the fifth slack variable in the original problem, or to the fifth constraint in the original problem being pushed to its limits. So complementary slackness tells you that since y5 is greater than 0, the fifth constraint over there must be actual quantity, so 1, 2, 3, 4, 5. It's 5x1 minus 5x1 plus 2x2 is equal to -3. What about t2 being bigger than 0? What does that tell you? X2 is equal to 0, yes. So like this, T2 is, well, it is a stack variable corresponding to the second dual inequality. Second dual inequality is about the coefficient f x2 being larger than the corresponding coefficient of x2 in the objective function. So the corresponding variable is x2. So x2 is equal to 0. And now you can solve it. X2 is equal to 0, hence x1 is equal to minus 3 over minus 5, 3/5. X2 equal to 0. And provided that we didn't make any mistake in between, this must be a feasible optimal solution to the primal problem. If we were to check it, we will check feasibility. Basically, we already checked complementary slackness. We just have to check feasibility. Maybe a kind of a simple test in between actually checking feasibility and checking that this is compute the value of the objective function. Objective function is minus 3/5, and here it is 3/5. So we did make some mistake. Oh, no. The objective function here, this w is 3/5, but this w is minus the objective function of the dual. So the objective function of the dual is minus 3/5, and it does correspond to the objective function of the primal, which is minus 3/5. So we do have the strong duality holding here. So it is some evidence that we did not make an arithmetical mistake in between. Yeah.
So kind of a dumb question, but just to verify, if you end up with in the dual, say that you have a slack variable that's negative, that would mean that your primal is infeasible. Is that correct? Or like if you somehow, if it's not 0 and it's not greater than 0, so that you can't really make any judgment about what
Okay, so if
x is in the primal.
If somehow you get the slack variable being negative in the dual, it means that you made some mistake in solving the dual. Because, the dual is about the constraints being satisfied and all the variables being positive. So both variables and the slack variables in the dual must be positive.
So they'll only ever be 0 or greater than 0.
Yes. It could happen that the dual problem turns out to be infeasible. It does have some conclusion about the original problem, so maybe let's discuss it. In this case, the dual problem is obviously feasible, the origin was feasible. It could happen that the origin were not feasible, you would try to apply the two-phase simplex method to the dual problem, it will turn out to be infeasible, and well, then you have to derive some conclusion. What conclusion? If the dual turns out to be infeasible, then the primal is so basically, okay, so maybe any suggestions? What can you conclude from this?
It could be unbounded.
Could be unbounded, yes.
It could probably also be.
You know that you have this weak duality theorem that any solution of the primal is a lower bound on all solutions of the dual. So if you have solutions of primal which are as large as you want, then there is no space for the solution of the dual to exist. It must give you some value of the objective function of the dual, but it must be larger than all possible numbers coming from primal. It could be unbounded. Unfortunately, this is not the only option.
Could it be also infeasible?
Could be also infeasible. So there are pairs of primal and dual which are both infeasible, and it doesn't contradict any theorems. So this, all the theorems tell you if the primal has a solution and if the dual has a solution, then something falls. But if neither of them has a solution, we have no theorems to talk about this. Or infeasible. Could it be both feasible and bounded?
No,
Why not?
there's strong,
Strong duality.
yeah, strong reality figure the other one would also have solution.
Exactly. So that's all the possibilities. The third possibility that it is both bounded and feasible would contradict strong duality. If it is both bounded and feasible, it would have an optimal solution, and this optimal solution will correspond to an optimal solution of the dual. But if the dual doesn't have an optimal solution, another option is so here, I mean, if you do arrive at this conclusion that the primal is either unbounded or infeasible and you do want to decide between the two possibilities, unfortunately you have to perform the first phase of the simplex algorithm on the primal to find whether it has at least one feasible solution. If it has at least one, you don't have to continue to the second phase of this. To the second phase, you already know that it will be unbounded. But so you will perform just the first phase of the simplex algorithm for the primal. Okay, also if the dual is unbounded, the primal is, well, this one is simpler. What it is? If you can have arbitrarily small values of the objective function for the dual problem. What can you say about the primal one? Infeasible, yes. So any solution of the dual problem is an upper bound on all solutions of the primal. If you had at least one solution of the primal, it must be smaller than all the corresponding objective function must be smaller than all possible values of the objective function for the dual. But if those can get arbitrarily small, then you don't have any space for a solution of the primal. So this follows from weak duality theorem. Yeah.
So for the complementary slackness, if a y is greater than 0, then you would find the corresponding constraint in Fisher's limit.
Yes.
And then if t is greater than 0, then you find the corresponding x and make it 0.
Mm-hmm.
Y is equal to 0. T is equal to 1.
So we didn't do anything with all the y's and all the t's that were equal to 0 because they will satisfy complementary slackness automatically. In their pair y, comma, corresponding slack variable in the primal, one is already 0. This one. So they don't give you any extra information. You only use the variables, both decision and slack variables, which are not reproducing.
So we don't really care if it equals 0.
It's not that you don't care. It's, I mean, complementary slackness just doesn't tell you anything new from this information.
So y1 is 0. What does that mean? Like, how does that, what kind of information is it?
So complementary slackness doesn't tell you any new information. So here y1 is equal to 0, well, you don't derive any conclusion. It might mean that the corresponding first slack variable in the primal problem might be non-zero. That's the only information that you get. But, you know, many numbers are not equal to 0, so it's not much information.
Oh, just a question on the pair thing. What if we have a variable that say x2 is basic in the primal, however its solution is 0. So in the dual, would its corresponding S3 still have to be 0 because x3 is basic? However, if x3 was 0, is there a possibility S3 would be something else?
So the question was, suppose that in the primal problem I get a dictionary where a basic, yes, where I have a basic variable, but it also happens to be 0. So, okay, so it will tell you that the
Will both be zero?
so it's basically about the degenerate solution of the primal, and then it leads to so there are kind of two notions. One is every dictionary for the primal gives you exactly one solution to the dual, which is optimal, which corresponds to just the coefficients in the last row of this dictionary, but then it will not tell you that this solution is unique. So basically, if you have a degenerate dictionary in the primal, like you described, where one of the basic variables is equal to 0, it will tell you that there is an optimal solution of the dual where the corresponding variable is 0, the dual variable is 0. But there might be also some solutions where it is not.
In the dual?
Yes.
Okay.
So basically, complementary statements you will be able to call them two different modes. Either both are equal to 0, or this is 0 and the other is not 0.
So you have to do the dual problem then, just to see if you get a unique.
So the complementary statements will be a kind of, usually the complementary statements will lead you just to one solution. In this case, it will lead, in the case you described, where the primal say has the general solution, it will lead you to the main solution to the dual one, which satisfy complementary statements. Out of those, you will have still to choose the ones which actually satisfy the dual problem. So in the space of all solutions, it is a linear space. You will have the region which corresponds to what the dual constraints actually hold. So, it is true that it will be simpler than the original problem. Actually, solving that you still have to do something like a simplex algorithm, but a smaller number of variables. So basically, it is both quite rare and more complicated. So I don't really want to go deep into this. Okay, so maybe what I do want to say about this thing is if the original problem, if the primal problem has a non-degenerate dictionary, the last dictionary is not degenerate, you can't make any degenerate operation on it, or all the basic variables are actually not equal to 0, the complementary slackness will produce for you exactly one solution of the prime, of the dual. If it is degenerate, complementary slackness might be kind of underdetermined, or might have infinitely many solutions. And just wait a second. Another thing is, this problem, sorry. So this problem did not ask you to solve the dual first. It just asked to solve the primal. So you should be able to recognize the situation. When the primal problem is in this form, you have few variables but lots and lots of constraints. You should automatically think about switching to the dual. It will save you lots of complications. See you next time.